us now recall what we have learned so far. We have introduced different classical ciphers: shift cipher, affine cipher, substitution cipher, Wegener cipher, Hill cipher, permutation or transposition cipher, play pair cipher. These are all block ciphers. And in block cipher, we encrypt in this way. Use the same key to encrypt each block of the plain text. X1 is encrypted under the key K, so Y1 is produced. X2 is second block. Each block is having same length. So second block is encrypted under the same key, and Y2 ciphertext block Y2 is produced like that. So this is your plain text string, and this is how we generate ciphertext string. Same key is used to encrypt successive plain text elements. And in string cipher, we have seen that from the given initial key, we generate a key string. And plain text string, suppose x1, x2 this, then the ciphertext string y1, y2, this produces this way. So encryption of x1 with k1, encryption of x2 with k2, like that. So block cipher is a special case of string cipher, where for block cipher every ki is essentially taken to be same key. Okay. So this already we have seen, these things already we have discussed. Now synchronous stream cipher, formally we are not going to define synchronous stream cipher. So already we have mentioned in synchronous stream cipher, the key stream is generated only from the key. It does not depend, this key stream generation does not depend on the plain text string or ciphertext string or both. Only it is derived from the key. This is synchronous stream cipher. Formally, so there is a key stream generator G that takes as input only the key and generates the key stream K1, K2, like that. Now, in synchronous stream cipher, we can formally define a synchronous stream cipher as a 6-tuple. Okay, so this, as usual, we have plain text space, ciphertext space, key space, encryption rules, decryption rules, and this L is the key stream alphabet. Okay, so this key stream alphabet, so GK, G is the generator, key stream generator. It takes the key and generates the key stream. And this key stream K1, K2, these are from the key stream alphabet L. Okay, so in some cases it may be different from your plain text space or ciphertext space or key space. So we define a key stream alphabet, extra thing, key stream alphabet we consider here. And as usual, for every key stream digit ki belongs to L, there exists an encryption rule EKI belongs to E, and the corresponding matching decryption rule DKI belongs to D, such that this condition holds. So EKI is function from plain text to ciphertext, and DKI is a function from ciphertext to plain text, such that this condition holds. So encrypted value, encryption under ki of x, when you decrypt it using the same ki, it will return you back the plain text x, and it holds for every plain text x belongs to P. So this is more formal way of defining a synchronous stream cipher. Okay, so it has this key stream alphabet and a generator, key stream generator. Wegener cipher, already we have seen, it can be defined as a synchronous stream cipher. Synchronous stream cipher, your keyword is the keyword is the, it's already we have discussed this. I am not going to discuss this again. And binary additive stream cipher. For binary additive stream cipher, it is also mentioned in binary additive stream cipher. We have plain text space, ciphertext space, and key stream alphabet. All are Z2. So elements consisting of 0 and 1. And encryption is simply bitwise XORing. This means Xi with Ki. So your key stream is also key stream. This Ki is the ith bit of key stream, and Xi is also a bit. So this is binary additive cipher. Okay. So essentially, encryption is there is a keystring generator. I have taken keystring generator G together with a state function A. String cipher we will see essentially string cipher is having certain memory. So there is a state function also. Okay, so this key is passes through this key stream generator and it produces the key stream Ki. At the ith time unit it is Ki, and corresponding Xi is XORed produces Yi. This is your binary additive stream cipher. So this way, as so this key stream generator, this may be your LFSR, and in that case this F is essentially this is G is your LFSR and F is the shifting property, the state function. The next state is initial state is holding each register holding the initial bit string, initial vector, and this shifting is done. So that is essentially the next step is defined by the shift function. Okay. So for if you use LFSR here, then the linear recurrence relation is used to produce this Ki. Okay. So this is your key stream generator. Okay, so for binary additive stream cipher, you take some key stream generator which produces key stream. This is 1 bit, and Xi is 1 bit of plain text and produces 1 bit of ciphertext. And decryption is simply same way you generate the ciphertext, generate the key stream, and XOR with ciphertext bit get the plain text. So this is your encryption rule. This is your decryption rule. So and since it is we are working modulo 2 in hardware, it can be efficiently implemented. Encryption, decryption, both the circuits you can implement using hardware in hardware modulo 2. Binary you are working with binary, so efficiently can be implemented in hardware. And as I said, you can generate this key stream using a linear recurrence relation of degree m. So this type of recurrence relation is used to generate your key stream. Initially k1, k2, k0, k1, km minus 1 is given. That is your IV initial vector, and after that km onwards for I greater or equal to m, you can generate this subsequently using this recurrence relation, where the CIs are bit strings. And since we are saying this is a linear recurrence of degree m, C0 must be equal to 1. C0 cannot be 0. Then otherwise this degree will be less than m. So we have already observed, we have discussed these things, how to implement, this can be efficiently implemented in as LFSR, this key stream. So hardware implementation of key stream, LFSR we have already discussed, and how it works, again it is written here, I will not go through this. And so these things you just go through, all these things, these are just repetition. What I want to discuss here, that synchronous stream cipher and non-synchronous stream cipher. So synchronous stream cipher already I have discussed. Non-synchronous stream cipher, as I said, when you produce the key stream from the initial key, it is this key stream generation not only depends on the initial key, it also depends on the previous ciphertext elements or previous plain text elements, or maybe depends on both. Okay, so ith digit of the key stream, it depends on, it may depend on x1, x2, xi minus 1, previous I minus 1 plain text, or y1, y2, yi minus 1, previous I minus 1 cipher text. So essentially, this is using memory. This is using memory. So stream cipher are essentially state cipher, also called state cipher, because it uses memory. Unlike block cipher is memoryless. Okay. So non-synchronous stream cipher is key stream is generated in this way. For example, I have taken this example from Stinson. So we have plain text space, cipher text place, key space, alphabet, key stream alphabet, all are Z26. And key stream we generate in this way. So key stream is K1, K2, K3 like that. So K1 is K initial key, and K2 is Xi minus 1. Means this should be Ki. Okay, Ki is Xi minus 1. Ki should be Xi minus 1. So K2 is X1, K3 is X2 like that. Okay, so encryption is simply addition modulo, addition of plain text digit and cipher key stream digit modulo 26, and your decryption is simply the reverse subtraction, cipher text digit minus the key stream digit, corresponding key stream digit. So one illustration, suppose your key is 8 and your plain text is this one. So corresponding to this plain text, you can get, you can encode it in a sequence of integers. So the association, already we have discussed this thing so many times. So we have 26 alphabets, A to Z, and each of them I can associate with a number from 0 to 25. So suppose this is my numbering, means A corresponds to 0, B corresponds to 1, C corresponds to, so that way D corresponds to 3, that way I assign. You know, general way I assign this. And according to that, this plain text is encoded as a sequence of integers in this way. R stands for 17, then E stands for 4, like that. Okay, you can write this corresponding to the, so plain text, you convert it into, you encode it, essentially it is encode it into a sequence of integers in between 0 to 25. So as I said, your plain text space is Z26. That is modulo integers modulo 26 elements from 0 to 25. We can associate in this way. So if you have a English text, you can convert it into a sequence of integers from 0 to 25 by assigning the alphabets with the integers between 0 to 25 in this way. So your key stream, as I said, key stream, how I generate initial, means K1 is K, given key, then K2 is this X1, K3 is X2, like that. Okay, Ki is, this should be Ki. Ki is Xi minus 1. So K1 is K, then K2 should be X1. So this way, if this is your plain text, your key stream will be, first one is 8, second one is this plain text, the third one is this plain text, fourth key stream digit is this one, like that. Okay, and the cipher text is simply this plus this modulo 26. Okay, you can generate this string and you can utilize this table, this table to get your cipher text. And decryption is straightforward. So you have this cipher text, corresponding integers you get this one. Now key stream, you know how this is auto key. This is your auto key cipher. So if you know the key, then from that key, you know the rule how to generate the key stream. So you can generate this key stream. Now you just subtract this minus this modulo 26. It will give you 17. 21 minus 17 modulo 26, 4, like that. So subtraction. However, this auto key, this is just for illustration. This is a non-synchronous. This is a non-synchronous or asynchronous stream cipher. Okay? This is an asynchronous stream cipher. And however, this cipher is not secure because your key space consisting of only 26 keys. So exhaustive search, it is means you can easily break by trying out all possible 26 keys. So it is not secure. But anyway, just to illustrate non-synchronous stream cipher how it works, we have taken this example. Next, what I will do, so what is the general model of stream cipher? Synchronous and self-synchronous stream cipher. We are going to discuss a more general way of designing stream ciphers. So before that, let me just go through this. So block ciphers, some points about block ciphers and stream ciphers, how they differ. Already I have discussed it 2 or 3 times. Let me once again go through this, summarize this. Block ciphers, in block ciphers, we process plain text in relatively large blocks. Each block size is at least 64 bits. Okay, so block lengths are block length is fixed, but it is taken to be not only 1 bit or 2 bit. It is at least 64 bit. DES already we have seen this is 64 bit. And same function is used to encrypt successive blocks. So in a successive block, same function is used to encrypt. In different modes of operations, we have seen that every plain text block is processed in the same way. And pure block ciphers are memoryless. If you consider pure block cipher, these modes of operations are essentially, they use memory. Say for example, OFB block, OFB or CBC, they use memory. I have this here, modes of operations I have. Let me once again go through. Just a minute. Modes of operations are, I have discussed most of operations from these nodes. So you can see that in CBC mode, while generating yi, you have to remember yi minus 1. So when you encrypt, this is encryption of xi using the key. Okay, so if you just see the picture, this x1, this block is encrypted. This block is XORed, passes through the encryption box, suppose DES, using the key, and it produces the ciphertext. And this ciphertext is we have to remember this ciphertext because it is used in the next iteration, processing the next block. Okay, so this is why means if you use the different modes of operations, it uses memory. But if you consider only one pure DES, okay, it is not pure DES, only one. This is the DES box. Only one plain text block you are encrypting. So this is memoryless. But if you use different modes of operations, it is it uses states. Means you have to remember this. You are outputting this value as well as you are remembering this because it is used in the next level, next iteration, in the next processing the next plain text block. Okay, so let us go through. So what to key? Okay, so block cipher, we are discussing block cipher, summarizing this. So if you use pure block ciphers, they are memoryless. Okay, pure means no modes of operations we are using. Pure block cipher, DES individually, DES or AES. On the other hand, if you see the stream cipher, in stream cipher we process plain text in blocks as small as a single bit. Already I have mentioned this. So this for block cipher, the block length is at least 64 bits. Generally, a block length n is taken to be very large. But for stream cipher, it is very small. Block length is very small. It is as small as a single bit. Okay. Encryption function may vary as plain text is processed and has memory, as it has memory. Encryption depends not only on key and plain text but also on current state. Say for example, we have seen that the encryption depends on the key stream, right? And that key stream, when I generate the key stream using LFSR, LFSR is holding some initial state, and then in the next state it is shifted. So the state is changed. So the registers, M-length LFSR, M registers in the LFSR means what is its current state. Encryption depends on that. Okay, encryption depends on not only the key and plain text, it also depends on the current state. Means what is the current state of your LFSR. It's the same cipher. That's why stream ciphers are also called state ciphers, because this has memory or state. Okay? And already we have discussed this thing. Adding a small amount of memory to a block cipher, as in the case of CBC mode, block chaining mode. Okay? So results in a stream cipher with large blocks. Okay, now general model, as I was saying, that we are going to discuss general model of synchronous stream cipher. So the general model is given by this thing. So you have some initial state. Sigma stands for state. Okay, sigma 0 is your initial state. This may be determined from the given key. F is the next state function. This is your next state function, and G is the key stream generator. Key stream generator. H is output function. Okay, so K1, K2, this is your key stream. X1, X2, this is your plain text string, and suppose Y1, Y2, it is your ciphertext string. I represent them in this way. Okay, so next state is generated by using this next state function that takes the current state and the key. So next state is generated using the current state and key. And the key stream is generated by the key stream generator. This is a key stream generator. It takes the current state and the key and generate the key stream. Ith digit, ith key stream digit. And output, how I generate output? Output means your ciphertext. Ciphertext, this H produces the ciphertext. It takes the key stream, ith key stream digit, and the ith block means ith digit here, plain text string, and produces the YI ciphertext. So this is pictorially, it's illustrated by this figure. So what we are doing, this generator is generating the key stream. So key stream Ki is generated using the key and the current state sigma I. So if it takes sigma I key, it produces Ki. And this state is updated. This next state function, it takes the key and this current state and produces the next state sigma I plus 1. So in the next level, it is your sigma I plus 1. Sigma I plus 1, G is taking key and sigma I plus 1 and producing Ki plus 1, like that. So key stream is generated in this way, and every time your state is updated. Okay, so when it is sigma I plus 1, F takes F and sigma I plus 1. It produces sigma I plus 2. So it gets updated. So this way the whole thing runs. So this F generates the next state using the key and current state. It produces the next state in this way, and G generates the key stream. This is the key stream generator. It uses current state as well as the key, and it produces the key stream. And this output function, essentially, this is the encryption rule. So Ki and Xi are these are the inputs of H, and produces Yi. So already we have, so you try to illustrate it with LFSR example. In LFSR case, we have used F to be shifting function. F to be shifting of your key stream digits, K2, K3, Km to the left. So initially your LFSR is holding K1, K2, Km. Okay, so K1, K2, Km and K1 is producing the output of the key stream generator. Output of the key stream, and then K2, K3, Km shifted one register, and the linear feedback Km, linear feedback, that is actually Km plus 1, it takes the position of Km. So everything here they are shifted left. So K1 is coming out as output, and K2, K3, Km are shifted once, and this Kmth position now is filled with Km plus 1. This should be Km plus 1. Okay, so this is this function by LFSR. You just think how actually you can visualize this LFSR based example by this generalized synchronous stream cipher. And key stream generator, as I said, key stream generator is, if this whole thing is essentially LFSR. So this consists of state as well as a generator, key stream generator. Okay, decryption is easy. Decryption simply you have the key. So this part will be same. You generate the key stream in this way. Okay, so this part is same. Decryption is you generate the key stream from the key and the current state, generate the key stream, and also update the next state. Okay, so F is taking the current state as well as key and updates the current state. Okay, and decryption, you just decryption means you have to apply the H in output function, inverse of the output function, H inverse. So H inverse takes yi and ki and it produces xi. So as I say that if you fix ki, means H is essentially H is output function. It takes xi, ki and xi. Now this function is invertible function if you fix this ki. If you fix this ki, then it is an invertible function. Okay, this function output function should be that. So H inverse ki comma yi will give you xi. So you apply H inverse. So this is the general model of any synchronous stream cipher. Why synchronous? Because the key you are generating only using the current key, only using the initial given key. It does not depend on the plain text values x1, x2 or cipher text, previous cipher text values k1, k2, y1, y2, yi minus 1, or previous plain text values x1, x2, xi minus 1. Okay, so it is synchronous stream cipher. So this is the general design, and LFSR, you can think LFSR, you can fit LFSR in this model, how you think about it. Okay, I've tried to explain it here, but just go through, you think more on it, and then you will get it, how actually this F and G are associated with LFSR example. And for binary additive stream cipher example also, this H function we take this H function to be, for LFSR also we take this H to be XORing function. This H inverse is also XORing. For binary additive stream cipher also we use XOR function. H inverse both are XOR function. Okay, so key stream you generate by running the key stream generator. Essentially F and G together forms the, this is your key stream generator. Whole thing is key stream generator. You generate the key stream, you update the state. Okay, you generate the next key stream like that. Okay, so key stream generator is given by this pair F and G. Okay, so if you consider the OFP mode, output feedback mode of block cipher, this is an example of synchronous stream cipher. Already we have discussed these things. Okay, just again check. This is a block cipher. This is this mode of block cipher is an example of a synchronous stream cipher. Okay, synchronous stream cipher. Because this key you generate using key stream you generate using the only the given key. It does not depend on the ciphertext, previous ciphertext values or previous plain text digits. Next is, okay, so synchronous stream cipher has several interesting features. So it has some good things as well as it has some bad things. The first problem is for synchronous stream cipher. The problem with synchronous stream cipher is both the sender and receiver, means the sender means encryptor and receiver means decryptor. Both must be synchronized. Both must be synchronized. You can see that whenever ith state is running here, for decryption purpose, ith yi is needed. Okay, so when you are using ki, this should be yi. So both sender and the receiver should be synchronized to allow proper decryption. Okay, and if in your ciphertext, if some ciphertext digits are inserted or deleted by an adversary during the transmission, okay, some ciphertext digits, suppose some ciphertext digits are deleted. So y1, y2, yn you are sending and yi is dropped, or suppose some yi prime you have inserted. Okay, so decryption will fail because of the synchronized property. Decryption will fail. So in that case, you have to resynchronize the whole system. Either you have to reinitialize the whole system, or place special markers at regular intervals in the ciphertext, etc. You can do resynchronization in this way. So you have to think of how to devise resynchronization techniques. You have to incorporate this. The good thing about this is you can detect the presence of an active adversary because of the synchronized property. Because you can, if some bits gets deleted or some bits gets inserted, so your decryption will fail because synchronization will be lost. And in that case, you can be certain that there must be some active attack going on. So presence of an active adversary means the adversary who can insert, delete or replay the ciphertext digits. Insert new ciphertext digits, delete some few ciphertext digits, or replace same ciphertext digits again and again is ending. So this the presence you can detect because of the synchronization property. So synchronization property, if you lost this synchronization, you have to resynchronize it, and the synchronization helps you to determine the presence of active attacker in the system. Another point is there is no error propagation. You can see that yi's, when we generate the yi's, they depends on only ki's, means xi and ki, but these keys are ciphertext independent or plain text independent. It depends on only the initial key, the key stream. This key stream depends only on the initial key. It does not depend on xi or yi. So if somewhere, suppose I have encrypted and encrypted the ciphertext string, you are getting this, and somewhere it gets altered, some y2s altered. Okay, so if it is altered, then it does not affect. So that alteration does not propagate. Means this effect, this does not have any effect on the other digits. So there is no error propagation. If somewhere error occurs, it will not propagate. So this is good as well as this is bad. Why? So modified ciphertext digits, suppose some ciphertext digits is modified. It is not altered. It is not deleted. It is just altered. Okay, some bit gets flipped in the ciphertext when transmitted. So it does not affect the decryption of other digits. because these ciphertext digits do not have any effect on the key string. Okay, so the next ciphertext digit will not get changed. There will be no effect on that. So modified ciphertext digits does not affect the decryption of other digits. So this is a good thing, but the bad thing is if an active attack is mounted, you cannot detect it, because active adversary might be able to make changes to selected ciphertext. So he can say this ciphertext positions I will change and check what effect I can get on the plaintext, corresponding plaintext digit. Okay, so this way he can mount an active attack. He is selecting some ciphertext digits and changing it and check what plaintext he is getting. Okay, so this type of active attack can be mounted without getting detected. You cannot detect it you cannot detect it because there is no error propagation. One bit, if it is changed by an active adversary, its effect is not it does not have any effect on the other digits. So you get this active attacker gets unnoticed. We cannot detect that there is an active attacker. So no error propagation gives me this disability. So additional mechanisms, you have to think of additional mechanisms to provide data origin authentication. That means from whom the data is coming, and data integrity guarantees, means whether the data is changed or not. So this, for these things, to achieve these things, this authentication and data integrity guarantees, you need to think of other mechanisms. So synchronous stream cipher, these are the advantages. Two main properties we have for synchronized stream cipher. One is synchronization needed between the receiver and sender. Another is no propagation of error. And both have their advantages and disadvantages. Okay, so this way. So this is your synchronous stream cipher. Now general structure of self-synchronous stream cipher. Self-synchronous, why means essentially it is asynchronous or non-synchronous stream cipher. But why we are using the term self-synchronous? Because means I will explain that. I will explain that why it is called self-synchronous stream cipher. So the general model is this. So your key stream generator, this is your state. It is a key stream is generated as a function of the key and a fixed number of previous ciphertext digits. So your key stream ki is generated using this key stream generator that takes the current state sigma I and key. That current state it depends on the previous, so this is ith step, so previous I minus 1 ciphertext digits. So it depends on yi minus 1, I minus 2, yi minus 2, t many previous ciphertext digits. So it depends on initial key as well as the previous ciphertext, t many ciphertext digits. And output is output means your ciphertext is generated using the output function on this ki and xi. Xi is the plaintext digit. Okay, so initially you have your sigma 0 initial state is we define this as yi minus 1. You take t equal to means sigma 0. Sigma 0 is taken to be y minus 1, y minus t. This is some initial. This is your initial state. This initial state is non-secret. It is initial state, and your key is given k, key stream generator g. H is the output function. This output function should satisfy the property that when we fix ki, then it is invertible. That means given ki, there exists a function h inverse as a h inverse ki comma yi giving you xi. So this is represented in this figure. So your key stream generator G takes the key and previous T many Y values. So this is ith digit key stream digit it is generating. So it will take Y I minus 1, Y I minus 2, Y I minus T. Okay, so it will take sigma I. Sigma I is consisting of I minus 1 previous ciphertext digits. So this is memory. This is using memory state. It is using state. So this is this T many ciphertext digits contributes in generating the key together with the initial key. The key stream is together with the initial key. And then normally as we do, you apply the output function on ki and xi and you generate yi. And this yi in the next iteration, this sigma is updated by this. So you are generating yi. So this yi will be put here. So in the next step, it will be yi minus 1, yi plus 1 minus t. So it is modified. Sigma I plus 1 will be simply I plus 1 minus t, I minus t, yi. Okay, so this value, once this value is generated, this is now put inside it. So this is shifted. So yi comes here, then yi minus 1, y means yi comes here, yi minus 1, I plus 1 minus t. T many values it is remembering. Previous t minus 1 ciphertext it is remembering. And next ki plus 1 is generated using these values together with this k. This way it operates. Okay, so why we call it self-synchronous? Because suppose some bit gets changed. If some bit gets changed after t many steps, so it will this yi suppose this digit is changed. So this is altered value. It is coming here the altered value, and this value consequently after t many times this value will be out. So the change in one this ith digit will affect the subsequent t many yi's, because when you generate yi plus 1, this change value is used. So until it is getting out of this memory, it will have effect on generating this yi's. Okay, so after t many values, I will have incorrect yi's, and after that it will be again synchronized. It will give you the correct result. So that's why it is called self-synchronous string cipher. Automatically it is synchronized. After certain time, it will be again synchronized. It will keep on giving you the correct result. If one digit is changed, its effect will be on some certain values. After that, it will again give you the correct answer. Okay. Decryption is simply you generate your key stream in this way using this yi. Using this yi memories, yi minus 1 previous, yi minus 1 values, t many values, yi minus 1, yi minus 2, yi minus t. These many values key stream generated, and this ki and yi, h inverse, we perform h inverse on ki and yi, get xi. Okay. So next it is updated by yi, and t many values, y t minus, or the initial yi minus t is will not be used in the next level. Will not be used. So yi, when it is yi, then it is yi plus 1 minus t. That way. And so this is most common presently used self-synchronous stream cipher is based on block cipher in 1 bit. It is based on ciphertext feedback mode. Self-synchronous stream cipher, self-synchronous, this is self-synchronous stream cipher, asynchronous. So this is CFB mode. CFB mode we have observed in CFB mode, if you consider this essentially CFB mode, this is essentially CFB mode if you consider block length to be 1. This stream cipher is essentially CFB mode. Okay, I have the slide CFB mode. If you remember the CFB mode, let me go through the CFB mode. CFB mode. So initial IV, this IV is essentially your initial state. So from initial state means only in the that general version of self-synchronous stream cipher we have used KI. We are generating using using T many YI value. Previous means YI minus 1, YI minus 2, YI minus T. T many previous ciphertext values, and in CFP mode we use only one value, just previous iteration, previous YI minus 1. Okay, so structure is same. Structure is same, only for general self-synchronous stream cipher, this Ki it uses not only Yi minus 1, it uses T many previous values. Yi minus 1, Yi minus 2, Yi minus T. Okay, so let me. So this comment is explaining that. Okay, presently used self-synchronous stream cipher is based on this CFB mode, cipher feedback mode, and there this CFB mode is similar to CFB mode. CFB mode, essentially in CFB mode we use only memory of size 1. We use memory of size 1. It is memory of size T state. T state. I mean, state is it is memory that we use T many value it is storing here. But normal CFB mode we use only 1 bit. Okay. Okay, so it is also having certain properties, nice properties, means advantages as well as disadvantages. So properties of self-synchronous stream cipher. Self-synchronization is possible if ciphertext digits are deleted or inserted, as the decryption function depends only on a fixed number of preceding ciphertext characters. So since as I explained, if some ciphertext digit is changed or inserted or deleted, its effect will be only on a fixed number of preceding ciphertext characters. So means if some ciphertext digit is altered, means or deleted or altered, its effects will be means the decryption function actually depends on a fixed number of preceding ciphertext characters, T many. So self-synchronization is possible. After T many steps, it will give you correct results. So capable of re-establishing proper decryption automatically after loss of synchronization. Once synchronization is lost, it will again can re-establish synchronization with only a finite number of plain text characters unrecovered. So some digit, ciphertext digits is altered, its effect then plain text digits, a few T many plain text digits you will not be able to recover. But after that, this synchronization automatically will be re-established and you will keep on getting the correct plain text while decrypting. Okay. The problem is these are advantages. Self-synchronization, you can make it self-synchronized. If synchronization lost, it can re-establish the synchronization. This is a good thing. But the bad thing is it is difficult to detect insertion, deletion or replay of ciphertext digits by an active adversary. Whether some active adversary is doing these things or not, you cannot detect that. So additional mechanism, you have to come up with additional mechanism to support this detection of active attacker. Required to provide additional mechanism is required to provide data authentication. Data origin authentication means from whom the data is received, and data integrity, whether data is altered somewhere gets altered. And another property, this is this self-synchronization property, one thing. Another property is limited error propagation. Error propagation, we have limited error propagation. Suppose a self-synchronous stream cipher, suppose a self-synchronous stream cipher depends on T previous ciphertext digits. Okay. If a single ciphertext digit is altered or even deleted or inserted, during transmission, the decryption of up to t subsequent ciphertext digits may be incorrect. As already explained this. Okay, its effect will be on t subsequent ciphertext digits, after which correct decryption resumes. Okay, so if in a ciphertext string, if one digit is altered, its effect is retained on means that error is propagates. That error propagates, but this propagation is limited error propagation. Up to t many decryption will be erroneous. After that, correct decryption will resume. Okay. As a result, what happens? Any modification of ciphertext digits, by an active adversary causes several other ciphertext digits to be decrypted incorrectly. Okay, so one position ciphertext digits, if it is modified, then by an active adversary, it causes several other ciphertext digits to be decrypted incorrectly, thereby improving the likelihood of being detected by the decryptor. Okay, thereby improving the likelihood of being detected by the decryptor. So active attacker, presence of active attacker, you can detect the presence of active attacker because you are getting decryption, incorrect decryption because of this limited error propagation. So because of limited error propagation, you can detect the presence of active attacker. Means not surely you can. It's not. It improves the likelihood of being detected by the decryptor. Okay, you can detect the presence of active adversary. Means your it is improving the probability of detecting the presence of active attacker because of this limited error propagation. And because of self-synchronization, it is very difficult. This self-synchronization property makes it very difficult to detect the presence of active adversary. Whereas this limited error propagation helps you to detect the active attacker. Okay, so this self-synchronization and limited error propagation, these two gives you means both we need in a trade-off. Both we need in a trade-off. Okay, so let us stop here. So in the next class, we are going to introduce public key cryptography. Public key cryptography, which is based on several number theoretic problems. Okay, so some number theory, I have to go through some number theory, basic number theory. So we will discuss those things in the next class. Here we have completed the symmetric key crypto systems, block cipher, stream cipher. Okay, symmetric secret key cryptography we have covered. In the next class, we are going to start public key encryption schemes. Okay, let's stop.